Hello students, welcome to the second video, section 1.7, where we're looking at limits at infinity and infinite limits. In the previous video, we looked at infinite limits, and so in this video, of course, we'll be looking at limits at infinity. This is a bit of a meatier video because there's a lot involved here. So please stay with it to the very end, and let's get right into it. So after all of that work, we have to develop an analytical procedure by which we can find limits at infinity. So that's what we're going to be doing here. So basically, a limit at infinity is describing end behavior of a function. What's happening on the right side, what's happening on the left side. We spent a lot of time talking about end behavior functions. So we want to find these limits at infinity. And again, we want to continue to keep this in mind. Limits at infinity describes the end behavior of a function. It's happening on the right side, it's happening on the left side. So in our first example, well, let's just read it. The limit as x approaches infinity. So let me pause right there because we're looking at this and I'm thinking, okay, since it's on the infinity side, we're talking about what's happening on the right end behavior. So what's happening on the right side? Well, because this function is a cubic function, so because the function is a cubic function, and the leading coefficient is negative, so -3 in this case, then the graph on the right side is going to fall. So since it's falling on the right side, it's getting equal to -infinity. So now looking at our second problem, we have initially the limit as x approaches -infinity. So, all right, -infinity, I'm talking about what's happening on the left side. So first we need to figure out what type of function this is. So an easy way to do this is, all right, I see -x squared, so that's going to be -x times -x, right there, times a positive x times a positive x. So I'm getting negative times negative is positive, so I'm getting this equal to positive x to the 4th, which looks something like that in the graph. All right, so since that's happening, so because the function is quartic, it's going to rise on both sides, which means our answer is going to come out to be positive infinity. So now I want to do our final example, the limit as x approaches infinity, so that's happening on the right side, of 3 minus 2x on x plus 3. So let's think about some of the things that we would talk about in pre-calculus. So since the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is going to be the coefficient of the numerator and denominator divided. So I have -2x on x. So -2 over 1. So the horizontal asymptote is going to come out to be equal to -2. So that previous example that we just did is going to give us a basis for developing our analytical process by which we can find horizontal asymptotes or limits at infinity for any type of rational function. So before we get into that, let's look at these two investigations. So let's think about these. I have 3 over x and I have 1 over x squared. So I want to talk about what does each of these functions have in common algebraically, and what do they have in common graphically? So the first thing I notice is that both functions are rational functions, where the degree of the denominator is greater than the degree of the numerator. The second thing that I notice is that both graphs have a horizontal asymptote at y equal to 0. So in pre-calculus, we learned 3 rules for determining the existence of horizontal asymptotes of rational functions. So when a rational function had a horizontal asymptote, the end behavior was always one such that as x approached negative or positive infinity, then the graph of f of x approached the horizontal asymptote. What we're going to do here is we're going to use the idea of a limit and calculus to find out why these rules are the way they are. So for each of these functions, we're going to divide every term in both the numerator and the denominator by the highest power of x that appears in the denominator. And then we're going to evaluate the limit and just see if the result actually matches out. So let's do that. All right, so here my highest power is x squared in the denominator. So I'll have the limit as x approaches infinity of x over x squared plus 2 over x squared divided by x squared over x squared plus 5x over x squared plus 6 over x squared. Okay, so now let's simplify these. The limit as x approaches infinity. X over x squared, I get 1 over x plus 2 over x squared, all over 1 plus 5x over x squared, so 5 over x plus 6 over x squared. All right, so it's been simplified. So let's substitute in infinity and see what happens here. So I get 1 over infinity in this first part. So 1 over infinity right here, that's going to be equal to, let's see, 1 over infinity, that'll get me 0. So 0, and then 2 over infinity squared, that's also going to get me 0. And then 1 plus 5 over infinity, that's 0. And 6 over infinity squared, that's 0. So I get this to be 0 over 1, which is 0. And that matches what I have going on the right end behavior. It is approaching that x-axis to the right. So now our second graph, let's look at this one. Same deal, I'm not even going to factor. The limit as x approaches infinity, divide everything by the highest degree in your denominator, so x squared. So I'll have 2x squared over x squared plus 7x over x squared plus 6 over x squared, all over x squared over x squared, 5x over x squared, and 6 over x squared again. Let's simplify this. So the limit as x approaches infinity, and 2x squared over x squared, that gets me 2 plus 7 over x plus 6 over x squared, all over 1 plus 5 over x plus 6 over x squared. Okay, so let's see what happens. So I'll get 2, and when I'm substituting in infinity, 7 over infinity, that's 0. 6 over infinity, that comes out to be 0. 1 plus 0 plus 0. Okay, so simplify this. So 2 over 1 gets me 2. And now let's check it against our graph right here. Yep, that is matching. As I'm approaching to the right, I am approaching this horizontal asymptote at positive 2. One more example, let's see what happens. Let's divide everything by the highest degree in our denominator, so x in this case. So the limit as x approaches infinity, x squared over x, 3x over x plus 2 over x, all divided by x over x minus 1 over x. Same thing, let's simplify. So the limit as x approaches infinity, 1 plus, sorry, that's not 1. That's going to be x plus 3 plus 2 over x, all over 1 minus 1 over x. All right, let's see what happens when I substitute in that infinity. So then I'll get infinity plus 3 plus 0 over 1 minus 0. All right, so infinity plus 3, that's going to get me infinity, over 1, which is infinity. So we're saying on the right side of the graph, because x approaches infinity, on the right side of the graph, the y values will approach infinity, which is what's happening because I have that slant asymptote happening right there, and the graph just keeps growing in that direction. So now let's look at what happens if we're approaching negative infinity. Okay, so same deal, we'll divide everything. So the limit as x approaches negative infinity of 2x squared over x squared plus 7x over x plus 6 over, sorry, that's x squared, 6 over x squared, all over x squared over x squared, 5x over x squared, and 6 over x squared. All right, so then we'll simplify that, the limit as x approaches negative infinity. And I'm going to get 2 plus 7 over x plus 6 over x squared all over 1 plus 5 over x and plus 6 over x squared. Okay, so let's see what changes from there. I substitute in negative infinity. So 2 plus, well, 7 over negative infinity, that's just going to come out to be 0. 6 over, well, negative infinity squared, that's just going to come out to be 0. Over 1 plus 5 over negative infinity, again, a very small number, close to 0. And 6 over infinity squared also comes out to be 0. Okay, so I get 2 over 1, which is equal to 2. And on the left side, yep, we are approaching 2 right here, approaching that same asymptote at 2. So it didn't really change much. Let's see if it changes our second one. So now the limit as x approaches negative infinity of x squared over x, 3x over x plus 2 over x, all over x minus 1 over x. Okay, let's simplify this. So the limit as x approaches negative infinity, I'm getting x plus 3 plus 2 over x all over 1 minus 1 over x. Now let's substitute in negative infinity. So I'm going to get negative infinity plus 3 plus 0 over 1 minus 0. So I get negative infinity over 1, which is negative infinity. And on the left side of my graph, as x is going to the left here, my y values are approaching negative infinity. They keep going down, which is confirmed in my graph. I keep going down right here, approaching that slant asymptote. So let's see what happens here. Does it matter? Well, it does not matter in the case when our function does have a horizontal asymptote. But when it has a slant asymptote, it will matter whether we're approaching positive infinity or negative infinity. So let's fill in these gaps. Graphically, a limit at infinity can yield a horizontal or slant asymptote. In pre-calculus, we discovered through observation that such a graphical property existed by comparing the degrees of the numerator and denominator. So from this point forward, this is not going to be a viable justification for the existence of a horizontal or slant asymptote. So what are we going to do to justify the existence of a horizontal asymptote using limits? Well, y equals a constant, y equals c, is a horizontal asymptote of f of x if and only if the limit of f of x as x approaches infinity equals c, or the limit of f of x as x approaches negative infinity equals c. So now let's actually apply this justification here. We're going to divide everything by the highest degree in the denominator, so x squared. So the limit as x approaches infinity of 5 over x squared minus 2 over x minus 2 over 3 plus 2 over x minus 3 over x squared. So that's what you get when you actually simplify everything. And so let's see what happens here. So substitute infinity in, I get 0 minus 0 minus 2 all over 3 plus 0 minus 0. Let's simplify and I get negative 2/3. So since the limit of h of x as x approaches infinity equals negative 2/3, then y equals negative 2/3 is a horizontal asymptote of h of x. All right, so everything that we've learned so far is going to work for any type of rational function, even stuff with radicals in the numerator or denominator. So let's look at this graph on the right side there. And I want you to say, okay, what is one thing that you notice that is different about the graph of this rational function versus the others that we have investigated in the past? Look at the graph and think about it. And hopefully you've decided that what's different is that I actually have two horizontal asymptotes. So with these two different horizontal asymptotes, let's look at the limit as x approaches negative infinity of 2x minus 2 over x, the square root of x squared plus 1. And so on the left side, I'm getting negative 2. And then over here on the right side, as I go up, I'm approaching positive 2. Well, that's interesting. Let's explore this further. All right, so let's do the same algebraic analysis that we did earlier. The only problem is when we actually approach negative infinity. So what I want to do is I want to think, okay, what is the square root of x squared? Well, that's going to get me x when x is greater than 0, which is what's happening when x is approaching positive infinity. So the limit as x approaches infinity of 2x over x minus 2 over x all over the square root of x squared over x squared plus 1 over x squared. So the difference here is in the denominator, I'm using, since we're still inside that square root, I can use that x squared. But in the numerator, I have to take the square root of x squared and use that one instead. So the square root of x squared is coming out to be x. Let's look at this further. So the limit as x approaches infinity, well, I get 2 minus 2 over x over the square root of 1 minus 1 over x squared. Now let's make my substitution. So I get 2 minus 0 over the square root of 1 minus 0. Or I get 2 over the square root of 1. Well, the square root of 1 is 1, so 2 over 1 is 2. So I am getting that same result on the right side for that graph that we saw on the previous page. Now let's look at what happens when I'm approaching negative infinity. So same start, but I need to say, okay, the square root of x squared comes out to be negative x. So it's the negative part of it when x is less than 0. So the reason for this has to do with when you take the square roots and then you have what's the order, what's the index of the radical, what's the exponent of what's the value of the exponent, and also it has to do with some absolute values. So all of that gets covered in algebra classes, but here what we need to know is that the square root of x squared is negative x when x is less than 0. So let's do this now. The limit as x approaches negative infinity of 2x divided by negative x in this case, minus 2 over negative x, over the square root, and this part won't change, x squared over x squared plus 1 over x squared. All right, so now let's keep going. The limit as x approaches negative infinity. Let's simplify this. So I get negative 2 plus 2 over x over the square root of 1 plus 1 over x squared. Now let's make our substitutions. So I get negative 2 plus 0 over the square root of 1 plus 0. And I'll get negative 2 over the square root of 1, which is negative 2. So on the left side, I have a horizontal asymptote at negative 2. So now I want to use this practice 2 more times just to get us some extra practice here. So I'm approaching negative infinity in both of these problems. So keep that in mind. So the square root of x squared comes out to be negative x since x is less than 0. So let's do this the same way. The limit as x approaches negative infinity, 3x over negative x minus 2 over negative x over the square root 2x squared over x squared plus 1 over x squared. Okay, so let's simplify. So the limit as x approaches negative infinity of negative 3 plus 2 over x over square root of 2 plus 1 over x squared. All right, so let's see what happens here. I make my substitutions and I get negative 3 plus 0 over the square root of 2 plus 0, which comes out to be negative 3 over the square root of 2. And we can leave it like that. If you want, you can rationalize that denominator by multiplying by square root of 2 on square root of 2. But it's not going to be necessary. That's mostly something that you do in pre-calculus and geometry. And now in calculus, that's a bit of an outdated method. So you can just leave it with a radical in your denominator now. Let's do our second example here. All right, so same thing. I'm approaching negative infinity and I have the square root of x squared in my denominator. So the square root of x squared comes out to be negative x when x is less than 0. All right, so let's do that division. So the limit as x approaches negative infinity of x squared over negative x plus 2x over negative x, all divided by the square root of 3x squared over x squared plus 2 over x squared. Okay, so let's simplify. So the limit as x approaches negative infinity, I get negative x minus 2 over the square root of 3 plus 2 over x squared. So let's make my substitution with negative infinity. So I get negative infinity, so positive infinity minus 2, which won't really matter, over the square root of 3 plus 0. So I get infinity over the square root of 3 equals infinity. Because it's not, if you take infinity, you divide it by anything, it's not really going to affect it. It still will be infinite. What I would encourage you to do actually is to graph both of these problems, and so you can confirm it in a graph, the results that we got here. This is going to conclude the entire module on 1.7. So by this time you've taken both of your quizzes and now you have a test review and a test coming up. So keep that in mind. You do have a lot of studying to keep moving forward. I would encourage you to really continue to practice these problems. And if you do need any help, I'm Mr. Hernandez, and this was Mr. Hernandez Teaches.